Check it out now, y'all.
NanoHub U, online instruction.
Hello and welcome back to NanoHub U's Bioelectricity Introductory course. In this lecture, I will conclude our first week's introduction to the nervous system by doing the derivation of the Nernst equation. So in the last lecture, in lecture 4, we talked about the resting membrane potential and how that resting membrane potential comes about because of two things. One, a concentration gradient from one point of the cell, or from the inside of the cell to the outside of the cell. And two, the fact that the membrane that separates the inside and the outside of the cell, that membrane is semi-permeable to that ion with which there's a concentration gradient. So in this lecture, what I want to do is I want to look at the mathematics that we can use to describe that phenomenon and the forces that are at play and try to derive an equation that will predict the membrane voltage for any particular ion concentration and membrane permeability. And we'll compare that to measured results. So when we spoke about those two conditions, the membrane permeability and the concentration gradient, we talked about how there's two forces that come about because of that. One is a diffusion force, or a molar flux of diffusion, that you would expect to see from an area of higher concentration to an area of lower concentration if the membrane itself permits that flow of those ions. And so the molar flux from diffusion is a known equation, and you can equate the flux from diffusion, m sub d, for diffusion, the molar flux is the m, the d is for diffusion, will be equal to the negative diffusion coefficient d multiplied times the derivative of the concentration with respect to x, where the concentration is a function of x, and x is the distance across the neuronal membrane. So if you have a higher concentration inside the cell than outside the cell, then you would expect the derivative of the concentration to be a negative slope. As you're moving from inside to outside, the derivative, the concentration goes from a high value to a low value. And so the slope, which is the derivative, that slope is going to be a negative number. So you have a negative number, and yet we know that the flux, the flow of those ions is going to go from high concentration to low concentration. So if the flux is going to be positive when we're going from high concentrations to low, when we have a negative slope, then we need to introduce this minus sign to give us a positive flux for a negative derivative. So we plot this concentration, which itself is a function of position inside to outside of the cell, as a derivative of that concentration with respect to that position, the negative, and then it's multiplied by this diffusion coefficient, which describes the ease with which the medium diffuses, the ions diffuse in that medium. So this equation describes the molar flux from diffusion. And a little note about equations in general. When you write an equation, when you do it on your homework, when you do it on an exam, always, please define each of the variables that you use. You don't have to do this every time you use them, but every time you introduce a new variable that you haven't defined already in that document, you define it. You define it right when you first use it. It's always difficult to read and understand the intentions and the understanding of a student as a teacher when you're grading, but it's even more frustrating when you're just a scientist or an engineer and you're reading a journal paper and you come across variables that are used without definitions. It's like acronyms being used without definition. The author always knows what it is that they mean, and maybe to a small subset in the community, it's obvious what is meant. But ideally, your work will have global reach or national reach or a larger reach than just your small group. And for that to be possible, you have to be able to explain what it is that you're trying to describe in terms that the largest number of people will understand with the smallest amount of effort. So please, always define your variables. One. The other point that I wanted to make is that when you look at a new equation, it's very easy to look at this and say, all right, I'm just going to memorize it. The molar flux from diffusion is equal to negative d dc dx. And I'm going to say that to myself 20 times, and then when I show up for the exam, I'll be able to regurgitate it. The problem with that is that in 10 years, when somebody asks you what's the molar flux from diffusion, you won't know. You'll have to go look it up. and you won't have any sense of intuitive understanding of what it should be either. It's much better to look at these equations, and it's not always possible. With some more complicated equations, there's just really no intuitive grasp, or at least not one that I've been able to grasp. But whenever possible, try to walk yourself through the equation and talk to yourself about what it is that the equation means and what those components in the equation mean. So the derivative of something is the slope. The derivative of the concentration gives you the slope of the concentration. And we know diffusion happens towards lower concentrations, so we can expect that introducing this minus sign will give us a positive flux when you're going towards negative derivatives. So the minus sign makes sense, the derivative makes sense, and the diffusion coefficient is just a constant that is proportional or determined by the medium in which you're located. So this equation should make sense to you intuitively, and if it does, you shouldn't have to memorize it. Okay, let's talk about the other flux. The other flux is the molar flux from electrophoretic effects. And with electrophoretic effects, what we're talking about is the electric field and the fact that opposites opposites attract and likes repel. So positive charges are attracted to negative fields, and negative charges are attracted to positive fields. Here we're dealing with a flow of positively charged ions, so those will be attracted towards negative fields. As the potassium ions flow out of the cell because of the previous flux, the molar flux from diffusion, they will increasingly leave behind negative anions and a negative local potential on the inside of the membrane to the positive local potential they're creating on the outside. Eventually, that'll make them want to move back in because the positive ions will want to go towards the negative charges and away from the positive charges. And that'll give you this molar flux from electrophoretic effects. Now, we expect this flow to be towards negatively charged ions. So towards negative voltages. So if we look at the voltage inside the cell and the voltage outside the cell, we can classify those as local potentials. So the local potential psi, we take the derivative of that local potential psi, and the derivative will give you the slope. It'll be positive when you're going towards greater potentials. So when you're going to more positive voltages, you'll have a positive derivative. But our potassium ions aren't attracted to positive, they're attracted to negative. So we'll want to take the negative again. So it's the negative derivative of the local potential with respect to distance across the membrane will give you the direction that the potassium ions wish to flow, and any positively charged ion wishes to flow in the presence of an electric field. And then we have two constants. One is the concentration, which we've defined previously, so we don't define it again on this slide. The concentration C. The higher the concentration, the greater the amount of flow. Those potassium ions are all affected by the same electric field. If you have a large number of ions all wanting to move, you're going to have more ions moving. If you have a small concentration of ions all wanting to move, you're going to have fewer ions. So the concentration directly affects the molar flux. And then finally, you have the mobility. The mobility is a constant like the diffusion constant, but it describes a different phenomenon. The mobility, mu, describes the mobility, the ease with which those ions can move in a medium. So if the intracellular or extracellular fluid is more viscous, your mobility is going to be lower. If it's less viscous, your mobility is going to be higher. So it's proportional to the fluid dynamics of the material that those ions are in. So now we have the molar flux from diffusion and the molar flux from electrophoretic effects. What is the total flux? The total flux of potassium, M sub K, is going to be the sum of the two fluxes. The flux that makes the potassium want to go out of the cell from diffusion, and the flux that makes the potassium want to go back into the cell from the electric field. So it's going to be the sum of MD and ME, and that will equal minus D, the diffusion coefficient, multiplied times the derivative of the concentration with respect to position inside to outside of the cell, minus mu, the mobility, multiplied times the concentration, multiplied times the derivative of psi, the local potential inside to outside of the cell, and the derivative, of that local potential as you move from inside to outside of the cell. So that is the total flux. But we're not really interested in the flux of those ions. We're interested in the electrical current. We're trying to get at what is the electrical voltage. And we know how to relate voltage with things like current and impedance. But we don't know how to relate voltage to flux. So let's talk, instead of flux, let's talk about current. So how does current relate to flux? Well, the current, I, is equal to the molar flux multiplied times the valence of those ions Z multiplied times Faraday's constant. So if you look at the units for molar flux and Faraday's constant, you'll find that they cancel out so that you end up with a number that is in units of coulombs per second. And that's the units for current. So Z is important because we have in some cases ions that are positively charged, in some cases ions that are negatively charged. Some cases ions with a single positive charge per ion, some cases ions with 2 positive charges per ion. So by introducing this Z valence number, it allows us to calculate the current of ions through the membrane, to a semipermeable membrane, for any ion, not just potassium. We'll keep talking about potassium for the purposes of this derivation, but this equation that we're working towards will be applicable towards any type of ion. So the current I is equal to mZf, which is equal to, we substitute the molar flux, the total molar flux, into this equation, and we find that the current I is equal to the negative Z, the valence, which is a constant, times F, Faraday's constant, this should be capitalized, multiplied times the diffusion D times the derivative of the concentration with respect to distance x, plus, because we've taken both of the minus signs out of the parentheses, plus mu, the mobility, multiplied times the concentration, multiplied times the derivative of the local potential with respect to x. And now we want to convert some of those variables to be able to simplify the equation. Specifically, we want to be able to convert the mobility into variables that are already present in the remainder of the equation to allow for that simplification. So the mobility is not a constant. Mobility is a function of the diffusion, d, the position, x, so mobility varies with position, the fluid, the viscosity, the environment varies with position. It's a function of x, and it's a function of 3 constants, Faraday's constant F, the gas constant R, and the temperature T. This is known as Einstein's relationship. And if we have Einstein's relationship, we can plug this in for the value of the mobility mu, and our current equation changes. So what we had before was minus ZF times the sum of D times the derivative of concentration with respect to X, and mu C times the derivative of psi, the local potential with respect to X. If we substitute Einstein's relationship for mu, and we simplify the equation, the current becomes equal to minus Z, the valence, F, Faraday's constant, D, the diffusion coefficient, multiplied times the derivative of the concentration with respect to X, plus the constant Z, the valence, times F, Faraday's constant, divided by R, the gas constant, multiplied times T, the absolute temperature, multiplied times the concentration C, and the derivative of psi, the local potential, with respect to X. So now we have an equation in which the current is proportional to the concentration and the local potential. And then we make a crucial observation. At equilibrium, the flow of potassium outside of the cell from diffusion will be equal and opposite to the flow of potassium ions into the cell from electrophoretic effect. And therefore, the net flow will be 0. And so the net current will be 0. So at equilibrium, the current, which is this equation that we've derived so far, will be equal to 0. And if it's equal to 0, then we can rearrange the terms on both sides of the equation to say that the derivative of psi, the local potential, with respect to x, will be equal to the gas constant times the absolute temperature divided by the valence times Faraday's constant. All of these are constants with a negative in front, multiplied times 1 over the concentration gradient times the derivative of the concentration gradient with respect to x. So the concentration, the local concentration as a function of x, that varies, right? As the potassium ions are flowing down out, the concentration will be dropping inside and rising outside. So this is a function of x, of where we are in position. And now we have a relationship between local potential, or the derivative of it, and local concentration, or the derivative of that. And that allows us to do an integral. So if we integrate across the membrane from the inside of the cell to the outside of the cell, and we integrate both sides of the equation, we take the integral of the local potential with respect to x is equal to minus RTZF. That comes out of the integral because it's a constant, times the integral of 1 over c dc dx. Therefore, integrating the left-hand side, this will give you the local potential inside minus the local potential outside, which is the membrane voltage. So we're getting there. Integrating the right-hand side of the equation, the minus RTZF has come out in front. The integral of 1 over c is the natural logarithm of c inside versus c outside. So this bracket notation denotes concentration. So it's the concentration, not concentration as a function of x, but now the specific concentration at the two endpoints of integration. So the concentration of potassium ions inside the cell divided by the concentration of potassium ions outside the cell. And it's divided because this is the natural logarithm of k inside minus the natural logarithm of k outside, but the natural logarithm of a minus the natural logarithm of b is equal to the natural logarithm of a over b. So that's what we've done here. And if you take that, then we already see that the local potential inside minus the local potential outside, that's how we've defined membrane voltage Vm all along. And that's now equal to this constant. We get rid of the minus sign by flipping the natural logarithm. So the natural logarithm of a minus natural log b is equal to natural log a over b. But the negative natural log a minus negative natural log b is equal to natural log b minus natural log a. So it's b over a. So we can switch it around, and we have the natural logarithm of the concentration outside divided by the concentration inside. And since these are constants, we find that this can simplify, and we can move the natural logarithm to a logarithm by just changing the value of the constant out front to 58 over the valence z, and the valence for potassium is 1. So it's 58 times the logarithm of the concentration of potassium outside divided by the concentration inside. And that can be written more generally as the membrane voltage is equal to the 58 over z times the logarithm of the concentration of any ion outside versus any ion inside, where that ion is an ion to which the membrane is semi-permeable. And that gives us Vm, which is the resting membrane potential for x, where brackets x is the local concentration of ion x. And that, in the blue hashed square box, that is the Nernst equation. And if you plug in the measured values of concentrations for potassium inside and outside the cell, it will predict a resting membrane potential of potassium of minus 65 millivolts, and it'll predict a resting membrane potential of around plus 20 millivolts for sodium. And you can take the values from earlier in this lecture and plug them into that equation and see for yourself. So, at the end of the last lecture, we talked about what would happen if you had a membrane and you switched and you were permeable at one point to potassium. So you'd have a resting membrane potential of minus 65 millivolts, and you switched. So the permeability, initially the permeability to potassium was high, much higher than the permeability to sodium. If we switch and the permeability to sodium goes up and the permeability to potassium goes down, the voltage will rise until you get to the resting membrane potential for sodium, ENA, where you start with EK, the resting membrane potential for potassium. You move up to ENA. If at this point you switch back and the membrane becomes semi-permeable to potassium again and not to sodium anymore, sodium will stop flowing through and the potassium ions will rush out of the cell, taking their positive charges with them, and drop the voltage inside the cell back down to minus 65 millivolts. And this rising and falling, this is what we call an action potential. And the transition is from permeability to potassium in these yellow regions to put permeability to sodium in this pink region and back. And that's how how it works. In fact, if you look at a measured action potential, you find that it's a little bit more complicated than that, because there's a little bit more than what we just talked about. So you have the base resting rate of about minus 65 millivolts, and when an action potential begins, the voltage begins to rise, and we call this the rising phase, until it reaches the peak value, the resting potential for sodium, and perhaps slightly exceeds that value for reasons we'll discuss further on in this course. That's the overshoot phase, and then begins to drop off in what is called the falling phase, where the permeability reverts to semi-permeable to potassium and not sodium. And then we have an undershoot, which we'll also talk about later on in week 4 of this course when we talk about Hodgkin-Huxley. You have this undershoot, and then you have this gradual restoration of the potassium resting membrane voltage of minus 65 millivolts. So that's the Nernst equation, and that's how we use it to predict the different values within an action potential. In week 2, we will begin to talk about the biochemical basis of these electrical signals. So we'll talk about ions, we'll talk about neurotransmitters, we'll talk about signal conduction in the membrane, and I'll look forward to seeing you next week. Thank you.